Bismillahirrahmanirrahim. So today, inshallah, we carry on our chapter 5, our MOS thing. So in very quick nutshell, so we did last time, we studied the behavior, the IV characteristic of the MOSFET when we have small values of VDS. We said that the channel will be created at what condition? When we create the channel between the source and drain, what's the condition?
Also the voltage.
What voltage?
The body, the center. Not the body.
We did not talk about the body.
The gate.
The gate, yeah?
Yeah, for the gate.
The voltage difference has to be more than the VGS or the overvalued value.
You are almost there, but still close. Yes, Mahmoud?
Yeah, the drain should be more than the...
No. The condition to create the channel.
To create the
The channel. We have to create channel first.
Yeah.
Before we have anything. So what's the condition to create the channel? This is a proof that you did not open the slides. Because it's not part of the quiz. And I told you, this is wrong. You have always to refresh. You have to always, when you finish, have a look and see.
I have 4 quizzes today.
Because there's the capacitance between VD and...
between the gate and the body.
Yeah.
Okay, good.
So
to create that capacitor, the other side of the capacitor is the channel. To create that side of the channel, what's the condition?
We need the voltage from the terminal.
Which terminal? What's that?
The drain has to be more than the source.
We are not talking about the drain and the source yet. We are talking only to create the channel. To exist, to have even a channel. The channel يعني قناة, to have like a wire, yes or no?
You need
so to create the channel, what's the condition?
Metal plate. Metal plate on between the channel.
Yeah, okay, so...
And pass a current through it. And pass a current through the metal plate.
No, of course not. The current should not come through the metal. Come from the channel.
It goes through the end pipe?
Yeah, of course. From the end to the end, from the source to the drain, through the channel. The channel to exist, what's the condition? And we are 100% sure that nobody revised. 100% sure.
Electrons should be in the...
Yeah, the condition to have the electrons in the channel. That's exactly the point, yeah. You're just rephrasing the question. Is to have VGS bigger than VT, bigger than the threshold voltage. VGS above VT. That's what we did here. Yes or no? That's the point. If VGS is less than VT, we have no channel. We have no business. We have no current between the source and the drain current is 0. Completely. That was the last slide actually. We talked about it before anyways. Just a quick refreshment. Good, let's keep going. So the point now, we increased the VDS a little bit, and we found that it will create a variable resistance for the channel, and that resistance depends on the overdrive. Yeah? Remember that? This is so the slope is actually 1 over the resistance between the source and drain, which is the resistance of the channel. And we said that resistance actually decreases as we increase the overdrive, because 1 over RDS actually increases. So if the slope increases, that means the resistance is decreasing. Yes or no? And that it is in function of the overdrive. As we increase the overdrive, that resistance decreases. And we represent it like a hose. So the overdrive, when it's small, we have a small, thin, small radius of a hose. خرطوم. As we increase the overdrive, الخرطوم هذا يكبر. Becomes bigger and bigger. So more water can go through. That means more current can go through. That means the resistance is less and less. As the resistance is less and less, the slope will be higher and higher. Okay? Simple. Good. So let's keep going. Now, today we add a little bit of complexity. As I've told you, if you don't revise, complexity over complexity will become a big problem. Good. So, what happens now to the current when we increase VDS higher and higher? Beyond what we call the small values. Because here the assumption is it is a small value. It means the electric field that is horizontal, not vertical, that of the gate, is really small compared to the vertical electric field that we discussed last time. So now, what happens when we increase VDS more and more, we'll see the limits, is that the relationship between the relationship that we did before between the voltage or the electric field is not anymore valid, and therefore the electric field, the horizontal electric field, will make sense. Will be like will be more pronounced. We cannot do the approximation that the horizontal electric field is smaller compared to the vertical electric field of the gate. So now in this case, how we can basically include this nonlinearity, because it will be nonlinear because the voltage of the channel will not be uniform over the channel. So what we do in this case, we do these steps. These steps are just to help us to understand the equation. So we don't have to memorize them. It's just to understand the equation where it comes from. We'll see. We start by assuming that VGS is held constant at a value greater than VT. Of course, because if we don't have this, we don't have a channel at all. That's the first and foremost condition. So we have to keep this inequality always there. Okay, so this is the first assumption. The second assumption is that VDS is applied and appears as a voltage drop across the channel. Meaning, so we'll see this. Here means that VDS, it will exist. There will be a certain voltage between the drain and the source. See, this is the transistor, if you remember, in one shot. Source and drain. So this voltage drop will exist through here. So before, we assumed that there is no voltage drop. Okay? The voltage here is all the same. Now, no, we say that no, there is a voltage drop, okay, here, from this place from the drain to the source, okay? Okay, so that's the second assumption. And we will note, basically because of this, that the voltage decreased from VGS at the source. So at the source, the voltage drop here between the voltage drop of the channel is actually VGS at the source. But at the end here is going to be VGD, okay? VGD, the gate to the drain, okay? So in this case, VGD, we can write it like VGS, and it's VG minus VS, minus VDS. So, because if you take this into perspective, so minus VS minus VS, they will cancel, yes or no? So we'll end up by VG minus VD, which is VGD. Yes or no? So that's the one. And basically that's it. So VGS is what? It's nothing but VT plus the overdrive. Yes or no? That's what we know, right? Because remember, VGS has to be above VT by overdrive. That's what we said last time, remember? Any question? Okay, good. So this is VGS, and this is what? VDS. So that's basically the gate to drain voltage. So this is what it is. So it's VT plus the overdrive minus the drop of the voltage between the drain and the source. So before, this was basically almost zero. VDS was almost considered as zero. Anyways, so this is the story. So now the channel behaves now in a different way. Based on what? Based on the voltages. So here, so first and foremost, we have this voltage VGS that is bigger than VT. And of course, there's no current. Is there any current? There's no current because here, the gate is isolated from the channel by the insulator. Yeah. That's why we don't have any current. So this is not surprise, okay? So we know that. So the only current that we are having here is the current that goes from the drain to the source. Great. Now, the channel, the charge, it will not be uniform when the drain voltage increases above small values, and therefore it will be here wider. Why is wider? Because the voltage the voltage here actually, the voltage differential between both sides of the N channel increases with VDS. So here the voltage is actually increases with VDS, okay? So it feels here more voltage, so therefore we have more charge than here, okay? And how much it lost? It lost a certain ratio with a proportional ratio with VDS, with a certain part, Here we have higher voltage than here. The channel here feels higher voltage than here. Why? Because this voltage and this voltage, they will compete each other, they will cancel each other, and therefore there will be only a little bit of voltage that will be sensed by the charge in the channel. Of course, here the bulk or the body is connected with the same potential like the source. Okay, so that we keep the three terminal configuration. Okay, so that's basically physically what's going on, and only in NMOS. So here so far we are dealing with NMOS. We have N, and then we have a P-type substrate. Okay, okay. We'll talk about the P-type substrate. So this is, I don't want to really take too much of derivation, which is not our really interest. So you don't have, if you want to go deep into learning how the derivation we have, we can discuss it in one-to-one. But this is just to show you how we can estimate the charge in the channel. Okay, the charge in the channel, you can take it as given like this, is equal now to the overdrive voltage minus half of VDS times L. Okay, all right. So that's basically the charge estimation in the channel. Because here, what we have, we don't have a rectangular shape. We just have a trapezoidal shape. Here we have القاعدة تاع شبه المنحرف, basically trapezoidal. It's written like this. trapezoidal ALR, يعني شبه المنحرف in Arabic. Okay, شبه المنحرف. So it has قاعدة. This is the great base, and this is the small base, and the volume or the number of charge or the quantity of the charge can be estimated using this formula. I don't want really to bother you too much about that. This is not our scope. We just get this given. Okay. All right. So let's keep going because we have to go to the industrial march. So let's see. So in a nutshell, so basically now what we are going to do. Well, remember here in the previous equation we have VDS small. We have this is actually V overdrive, right? So now the overdrive will be replaced with the overdrive minus half VDS. Okay. We'll explain it when we have time why we need to do that. And VDS stays there. So then we take this equation, just multiply basically our what we did. Basically, we just took off this, and that's it. Here, the question here, the condition to write this is that VDS has to be smaller than the overdrive. So the condition to be able to do this is that the voltage from drain to source has to be less than the overdrive. Okay? Now, if VDS is bigger than the overdrive, we have to replace, we have to do that. We have to use this equation. But this equation is the same as the other one. Oh, hold on a second. Oh, here we go. Okay. There's, I think there's a type. Yes. Okay, otherwise, if it is. Oh, okay. Okay. All right.
There's no half.
No. Here, actually, there's an overdrive here. There's a typo here, actually. If VDS is less than the overdrive, here you VDS will be written like this. But if it is above, otherwise means VDS is above V overdrive. So in that case, you have to replace VDS by the overdrive. You see here? So this becomes V overdrive in that case. Okay. So in our case, so if we take these two set of equations, we have these two set of equations. So if VDS is less than the overdrive, we use this equation. If it is above the overdrive, we have to replace VDS by the overdrive, and in that case you get this thing. Because V overdrive minus half of V overdrive will be half of V overdrive, yes? And times V overdrive will be half V overdrive squared. Yes or no?
Yes.
So basically what we want to say here is that now the current in the channel or through the transistor will behave according to this set of two equations. There is this, the equation here applied only when VDS is less than the overdrive. when VDS is above the overdrive, the current will take the shape of this equation. Okay? So this zone means VDS when it is less than the overdrive, we call it the triode. Okay? The triode region or the triode zone. And here, when the VDS voltage is above the overdrive, the overdrive voltage, so VDS is bigger than the overdrive, in that case, we are in the saturation region. We will see what we mean by that in a second, so don't worry about this, okay? Alright, so this is basically in a nutshell what's going on. So this is the triode region. As you can see in this equation, the equation that describes this nonlinear behavior is this one. Excuse me. So as you can see, this equation is quadratic in respect to VDS. And this is x. VDS square we have here. Okay? So basically that's the the equation of this curve. Okay? Alright? So it is proportional, the current ID is proportional to VDS quadratically, which is this term, VDS times VDS. Okay? This one is the first order, VDS times the overdrive, okay? So this is the triode region, and the saturation region here, why we call it saturation region? Because in this equation, there's no parameter that is VDS. All the parameters here are independent of VDS. So that means ID is completely flat compared to VDS. So it's independent of VDS, and this is really interesting when we discuss it later on, okay? So this region now from here, so VDS, so that's why we call it here VDS saturation, means the maximum or the limit between the triode and the saturation. So in here, from here on, we are in the saturation region. From here below, we are in the triode region. So the saturation, VDS saturation, means the limit between triode and saturation, is actually the overdrive. That is the limit, okay? So we'll see further, we'll discuss further. This is just to explain primarily the operation. I think, let's stop now because we don't have time. Let's stop now here at this point. I think we have just a couple of slides and that's it. So yeah, a couple of slides. And we'll continue inshallah next week when VDS is away than the overdrive, and we'll talk about the behavior further. Okay?
So on Sunday we'll have the test, right?